So just now your friend asked me a question in the lift. In talking about electron neutrino, muon neutrino, tau neutrino, we introduced the three electron numbers. So we introduced three electron numbers and said all interactions should conserve each of them individually. But if I now say that mu e is oscillating into mu, initially I have a state with Le equal to 1, L mu equal to 0, and finally I have a state Le equal to 0, L mu equal to 1. So both Le and L mu are not conserved. Though mind you, the sum Le plus L mu is conserved. So, which means that neutrino oscillations are actually violating the individual electron number conservation. And to some extent that is sort of built in when I say that mu e is a linear combination of mu1 and mu2, and similarly mu is a orthogonal linear combination of mu1 and mu2. And if you based on your study of addition of angular momentum, for example, you have the states which are eigenstates of L and eigenstates of S, and in some sense they are sort of orthogonal eigenbases. But I need to consider the eigenstates of J, which is L plus S, when there is this so-called spin orbit interaction in the atom, when the Hamiltonian contains L dot S. So that L dot S is linking these two orthogonal states through that making the orbital angular momentum interact with the spin angular momentum. Therefore, I am compelled to consider the eigenstates of L and S, rather L plus S together. In a somewhat hand-waving way, we are talking the same thing, that there is an interaction. I don't know what it is, but there is an interaction which is coupling mu e to mu, and because of which I have to diagonalize that interaction, and diagonalizing that interaction gives me these eigenstates mu1 and mu2. So that is the sort of background view. What that interaction is, I am not explicitly telling you because I don't know it myself. But I am assuming there is such an interaction, and diagonalization of that gives rise to these mass eigenstates mu1 and mu2. Therefore, my original states mu e and mu I write as linear combinations of mu1 and mu. But this actually raises other questions. So, this is one of the very important things in quantum mechanics. Either a quantum number is exactly conserved or it is not. Of course, we do have the idea of approximate symmetry and we exploit it, but we say Le is exactly conserved means all interactions which violate Le are forbidden. But if we allow for the possibility that Le is not conserved, then in principle all other interactions where Le is not conserved are also allowed. In particular, if this occurs, in principle, this also should occur. So, now my challenge is to build a form of the nu e, nu mu and electron muon interactions in such a way that this occurs at the observed level, whereas this does not occur at the current level. Right now there is a upper bound of 10 power minus 13 or so. So which means that this occurs means this also occurs, but let's say this occurs at the level 10 to the minus 15. Then I satisfy the experimental bound on this and I explain this. So this is the challenge of constructing a method of the lepton interactions which can explain all experimental data. And over the last 25 years or so, this has become a subfield called neutrino mass building, rather neutrino mass model building. And there are literally hundreds of models available, but none of them is particularly compelling. Okay, some have more attractive features compared to others, but none of them is compelling. And people that way are experimentally, people are devoting a lot of effort to this, and also a related decay called mu to E conversion. A muon cannot spontaneously turn into electron because of energy conservation, but this we discussed in a previous class. A photon spontaneously cannot go into E plus E minus pair because of energy momentum conservation, but in the field of a Coulomb nucleus it can. So rather, in the Coulomb field of a nucleus it can pair produce. In a similar way, if I have an atom where an electron is replaced by a muon, then this conversion becomes possible because the Coulomb field of the nucleus, it can absorb the necessary momentum, and then you will have something like 100 MeV electron shooting out if this conversion takes place. So there is an experiment. There are of course neutrino oscillation experiments at J-Park in Japan and at Fermilab in the US. Parallelly, in both places, there are these mu to E conversion experiments. For some technical reasons, it is felt that there is a better chance of observing this conversion rather than this decay. So people are concentrating on this mu to E conversion. So if we have a positive number either for this or for this, that will give a huge boost to this, to identify how that interaction between the different flavors, how it is taking place. Okay, in the last class we talked about two-flavor vacuum oscillations. Now let us go to three-flavor vacuum oscillations. But before that, let us look at the two-flavor oscillations from a slightly formal point of view. So I have two states nu e and nu mu, and I said those two states will mix to form two other states nu1 and nu2, and the relation between them is given by an orthogonal matrix. And I said this matrix should be orthogonal based on probability conservation. However, note that these are fermion fields, and fermion fields in general are described by complex objects. So, when my eigenstates are complex and I want to preserve the probability, what is the property of the transformation matrix? I have one set of eigenstates, psi I, and I want to write them in terms of another set of eigenstates, phi j. So the matrix that's connecting them should be a unitary matrix. So why did I choose an orthogonal matrix? Let us discuss that first. Let's consider an n by n orthogonal matrix which has n square real numbers. It's an n by n matrix, so there are n square real numbers. And so does it mean that I have to specify n square real numbers to construct the orthogonal matrix? Obviously no, because orthogonal matrix satisfies this constraint. O transpose O is identical. But O transpose O is a n by n matrix. And identity, of course, here is also an n by n matrix. So this equation, this matrix equation, is actually a set of n squared equations. So it looks as if I have n squared equations and I have n squared real numbers and n squared equations connecting them. So there can only be a unique solution. Is that correct? No. See, remember, I wrote O. O is not unique because theta is not specified. So there is no unique solution. But naively speaking, there are n square equations and n square numbers. So, and actually these are n square linear equations between n square real numbers. So naively it seems as if there should be a unique solution. So obviously there is a catch. What is the catch? Obviously these n squared equations, they are not all independent. And you can show that O transpose O is a symmetric matrix. You take the transpose of this and you get this back. Since it's a symmetric matrix, how many independent equations are there? So then there are n diagonal equations. The diagonal elements are all equal to 1, so there are n such constraints. And how many other constraints are there? How many independent off-diagonal constraints are there? N square minus n by 2. There is another name for n into n minus 1 by 2. You come across it in combinatorics. In combinatorics, what is n into n minus 1 by 2? NC2. And I can make another argument as to why this should be NC2. By the way, this is NC2, but so there are n square numbers and n plus n square minus n by 2 constraint, and this is n square plus n by 2 constraints. So, which implies n square minus n square plus n by 2, which is n square minus n by 2, which is NC2, 3 parameters. So, to specify an n by n orthogonal matrix, I need to specify NC2 free parameters. And when n equal to 2, 2C2 is 1. So, a 2 by 2 orthogonal matrix has one rotation angle. When n equal to 3, 3C2 is 3. And do you have a physical example where this happens? In classical mechanics, for example, Euler angles. To define an arbitrary rotation, I need to specify 3 angles. Those are, and Euler gave a prescription as to how to do that. And when n equal to 4, 4C2 is 6. So, do we have an example from relativity where this number is relevant? No. Okay, field strength tensor is a symmetric matrix, 4 by 4 symmetric matrix, but I'm talking about 6 parameters. To specify the most general Lorentz transformation, see, most general Lorentz transformation is of this form. x0 prime, x1 prime, x2 prime, x3 prime is x0, x1, x2, x3. And to specify this lambda, I need 6 parameters, not 4. Sorry. It's a 4 by 4 matrix. I need 6 parameters. So I do the classification this way. There are transformations which change. I'm talking about what is called the most general Lorentz transformation, where there are transformations which change the time coordinate and there are transformations which do not change the time coordinate. What do we call the transformations which do not change the time coordinate? x0 prime is x0 and x1, x2, x3 go into x1 prime, x2 prime, x3 prime. Rotations. And we just discussed that there are 3 such things. And now consider the set of independent transformations which change the time. How many are there? 3. One involving x0, x1, one involving x0, x2, one involving x0, x3. So 3 plus 3 is 6. The most general Lorentz transformation, I need to specify 6 quantities. And this also tells us another way to derive this NC2. See, we want this O is a rotation matrix, and what is the simplest rotation that we discussed? Simplest rotation involves two variables, x1, x2 go to x1 prime, x2 prime, and that involves one angle. And how many independent simplest rotations can I construct if I have n variables? I have total n variables, and each simplest rotation requires two variables. No, not n by 2. I have n variables, and one simplest rotation requires two variables. So how many independent simplest rotations can I construct? I have to choose 2 out of n. And how many ways can I choose? NC2. So that's another way to argue that the n by n orthogonal matrix requires NC2 parameters. Now let us look at an n by n unitary matrix. This has n square complex numbers, which implies 2n square real numbers. But once again, U is not the elements of U are not completely independent. There are constraints, so I need to worry about the number of constraints. So I have U dagger U is equal to identity, and I get n square constraints. U dagger U is again an n by n matrix, and again I have to worry how many of these n square constraints. I have to worry about two things. How many are dependent on each other? So how many independent constraints? That is number one. And number two, out of these independent constraints, how many are real constraints and how many are complex constraints? So, and as I just mentioned that O transpose O is a symmetric matrix. Similarly, you can prove that U dagger U is a Hermitian matrix. So, what can you say about the diagonal elements of a Hermitian matrix? They are real. So, the diagonal constraints, how many are n? The diagonal constraints how many do I have, and are they real or complex? I have how many? N real constraints. And off diagonal n square minus n off diagonal constraints, but are they independent? Yeah, they are complex conjugates of each other. So, if I treat one set as double the number of real constraints, then the other set are not independent. I mean, if I say x plus iy equal to 0, it means x equal to 0 and y equal to 0. Then there is nothing, I don't get an independent constraints from x minus iy equal to 0. So, off diagonal constraints I have n square minus n by 2, that is the number of constraints, but each is equivalent to 2 real constraints, or let me write independent complex constraints. So that is equivalent to n square minus n real constraints. So n here, n square minus n here, so total n square constraints, and total number of real parameters is 2n square. So I need n square real numbers to specify a unitary matrix. By the way, in physics, we really love what are called special unitary matrices, where we have an additional constraint that determinant of u is 1. So, to specify a SUN matrix, I need only n squared minus 1. So, when n equal to 2, I need 3. Those are the 3 Pauli matrices. And when n equal to 3, I need 8, which are the Gell-Mann matrices in quark model. And now we sort of come to parameterization. At least in physics, we choose these n square numbers. We prefer to classify these n square numbers as angles and phases. So, we write this n squared as n square minus n by 2. Huh?
It should be n real numbers, right? Because total constraints are
No, total constraints are n square minus n.
yes.
Sorry, n square minus n plus n. So there are n square constraints. So this many angles plus so for n equal to 2, we have one angle plus 3 phases. So let me write the 2 by 2 matrix as cos theta e power I alpha minus sin theta e power I gamma sin theta e power I beta 1 angle and 4 phases, but I'm over counting, and in writing like this I have partly ignored the fact that U is a unitary matrix. If I put the unitarity condition, for example, complex conjugate of this times this plus complex conjugate of this plus this should vanish. If I impose that condition, I will get delta in terms of the other 3 angles, and in fact we will get delta is equal to minus alpha plus beta. Yeah, this is the condition we get. Minus alpha plus beta is equal to minus gamma plus delta, or delta is equal to beta plus gamma minus alpha. So let me write that. Having done this, now I will rewrite this as, minus alpha. I pull e power I alpha out from the first row. Then I have cos theta times sin theta e power I beta minus alpha minus sin theta e power I gamma cos theta e power I gamma plus beta minus alpha. This matrix I can write like this. And now I pull out e power gamma from here and put it here. So if I pull e power gamma out, you see that the phase here is 0, phase here is 0. Phase here is beta minus alpha, phase here is beta minus alpha. And now this phase I pull out on the right hand side. The common phase of the second column I pull out on the right hand side. So you see that the most general 2 by 2 matrix, 2 by 2 unitary matrix, I can write as a phase matrix on the left hand side times purely a rotation matrix times a phase matrix on the right hand side. So, and remember, where is this matrix occurring? this matrix is occurring in the relation between two sets of complex fields. So, I transfer this matrix to this side and absorb the field alpha in nu e and gamma in nu mu. And similarly, this phase beta minus alpha, I absorb it into nu 2. So, and if I change the phase of a field by a constant amount, this is what we learned from quantum mechanics, that does not affect the dynamics. So, these phases are unphysical. There is no way we can measure them in an experiment. So, the physical quantity is just the rotation angle. So, in considering 2x2 mixing, the flavor oscillations in the two-flavor approximation, there is nothing goes wrong if I take the mixing matrix to be orthogonal. I don't have to consider the unitarity. However, that is not the case when we do the three-flavor mixing. Here, U is a 3x3 unitary matrix. So, this has three angles plus 6 phases. If you look at the formula that we wrote down. So, let us try to start pulling out the phases as we have done in the 2x2 case. Of course, putting these 6 phases, distributing these 6 phases among the 9 elements in a way to satisfy unitarity, you need to do a little bit of algebra. It's not very straightforward, but if you struggle with it for some half an hour or so, you will find you can do that. But we don't need to do all that to understand the argument. So, just as before, I put 9 moduli and 9 phases in the 3x3 matrix as I have done here. Now, from first row I pull out a phase, then second row I pull out a phase, and from third row I pull out a third phase, so that my first column is now purely real. Okay, which means that there is no phase to be pulled out from the first column. So on the right side matrix, the 1, 1 element will be 1. Then from the second column, I pull out the phase of the 1, 2 element. The first element of the second column, the 1, 2 element, now it has some phase. I pull that out common from the second column. Similarly, the 1, 3 element is the top element of my third column. It has some phase. I pull it out. So, the right side matrix will be 1, some phase, some other phase. So, this business of pulling out phases allows me to pull out n phases on the left and n minus 1 phases on the right. So, in the case of 3x3, I can pull out 3 phases on the left and 2 phases on the right, which means that one phase must remain embedded in the matrix. There is no way I can pull it out. And if it remains embedded in the matrix, it is going to affect my neutrino oscillation probabilities. And so, if I make a careful enough measurement of my neutrino oscillation probabilities, I can find the value of this phase. So, in the 3x3 case, I cannot make my mixing matrix to be real. There is one phase which definitely should be there in the mixing matrix, and it is going to affect my oscillation probabilities. And this has important consequences for the various physics studies, and I will briefly discuss that now. So we have in the 3x3 case, we have mu e, mu u, mu tau. Which is a function of 3 angles and 1 phase times mu1, mu2, mu3. And people write this matrix in two different ways. In one case, we use this parameterization. We write so this 1, 2 means the rotation is confined to first, second row, first, second column, third row and third column are trivial. 1, 3 means rotation is confined to first and third rows and third columns, second row and second column are trivial, and similarly here. And this first rotation, the two outward rotations, they are purely real, and the middle one, that is a complex rotation, and you see that by putting the phase in the middle, we ensure that it cannot be pulled out. And explicit form of this would be 1, 0, 0, 0, 0, C23, S23 minus S23. Please pay attention to the where the minus sign is there. We follow the same convention as in the two-flavor oscillations. And another way people usually write this, it's not quite a parameterization but just a notation. The 1 1 element is called UE1, similarly UE2, UE3, UMU1, UMU2, UMU3, U-tau1, U-tau2, U-tau3. This is actually a very useful notation because the physical meaning is very clear here. UE1 is the overlap between electron neutrino and the mass eigenstate 1. Similarly, UE2 is the overlap between electron neutrino and the mass eigenstate mu2. Similarly, U-tau2 is the overlap between nu tau and the mass eigenstate mu2, etc., etc., etc. And you can verify quite easily that the three angles are defined. If I define my matrix like this, you find that UE1 is cos theta 1 3, cos theta 1 2, UE2 is cos theta 1 3, sin theta 1 2, UE3 is sin theta 1 3 e power minus delta, u mu 3 is cos theta 1 3 sin theta 2 3, and u tau 3 is cos theta 1 3 cos theta 2 3. And these four elements, u mu1, u mu2, u tau 1, u tau 2, they have much more complicated dependence. If you sort of go and look up your Euler Euler matrices, you find that one row depends on two angles, one column also depends only on two angles, and other four elements necessarily have all three angles, and that is what is reflected here. So, in some sense, if I measure UE1, UE2, UE3, u mu3 and u tau 3, I can measure all the angles and also the phase. Now, let us consider the oscillation probability in the case of two-flavor oscillations, rather three-flavor oscillations, and I will use a sort of a general notation. Let us assume that I produce. By the way, this is another notation which is used in neutrino physics. The flavor states E mu tau are represented by Greek indices, and the mass eigenstates 1, 2, 3 are represented by Roman indices. This is a notation which is become quite standard in neutrino physics. So, some decay has taken place and it produced a neutrino in the flavor eigenstate alpha. So this is the neutrino at time t equal to 0. But by assumption, this state is not a mass eigenstate. So the free particle eigenstates are the mass eigenstates. So I should expand it as a linear combination. So this is u alpha 1 mu 1 plus u alpha 2 mu 2 plus u alpha 3 mu 3, and if you want I can write it sum over I u alpha I mu I. At time t equal to 0 I should. So at time t, this state is sum over I u alpha I e power minus ei of t, or rather let me write an extra step, mu I of t, but time evolution of nu I t just involves, so sum over I u alpha I e power minus I e I of t mu I of. And now, so the amplitude for a state which started out as nu alpha to be in the flavor eigenstate nu beta at time t. By the way, beta can be alpha, in which case I have a survival probability. If it is different from alpha, I have an oscillation probability. This is sum over I u alpha I and if you work this out from the definition, this number is mu e, mu tau, mu 1, mu 2. So based on this definition, if you work out what this overlap is, you will find that it is sum over I u alpha I u beta I star e power minus I e I. By the way, please note that here you understand what is called Einstein summation convention. I am not using Einstein summation convention here because up to here I is occurring only twice, but here I is occurring 3 times. So Einstein summation convention is a very powerful technique as long as you follow the rules of it strictly. if you are careless, you can prove anything you want. You can prove 1 equal to 2 using that by misusing Einstein's summation convention. And one of the important rules of Einstein's summation convention is an index should occur either once or twice, never more than twice. If you put an index more than twice, it means you made a mistake. However, here the index I is occurring 3 times. It's not that we are making a mistake, but the dynamics is such that the index I is occurring 3 times. So, to avoid making a mistake, I am explicitly putting this summation over I. So, there is no summation assumed as in the case of the Einstein summation convention. So, we have the amplitude, square of it is the probability. This is a summation, and in general it's a complex number. So I have to take the mod square. So I take the complex conjugate of that, and now I put the summation over j, because this I, since I am doing the summation over I actually is a dummy index. So to avoid confusion and making a mistake, I now put the summation over j, and u alpha I star, u alpha j star u beta j e power plus I dj. So there are cases where I is same as j, and there are cases where I is different from j. We will consider each separately. First, we consider the cases where I is same as j. So let's take I to be 1 and j also to be 1. There are 3 terms here, 3 terms here. So when I multiply, I should get 9 terms. So first term, I take I to be 1, j to be 1, and I get u alpha 1 mod square, u beta 1 mod square. And similarly, when I equal to 2, j equal to 2, I get u alpha 2 mod square, u beta 2 mod square, etc. Okay, let me just write it down. And now the cross terms. So I take I equal to 1, j equal to 2, and then I take it along with, or let me just write it down. So I get u alpha 1, u beta 1 star, e power minus I e1 t, u alpha 2 star, u beta 2, e power plus I e2 t, plus, now I take I equal to 2, j equal to 1, so I have u alpha 2 star, u alpha 2 beta 2 star, e power minus I e2 t, and u alpha 1 star, u beta 1, e power I e1 t, and then plus the so-called 1, 3 terms plus 2, 3 terms. There should be 9 terms. I have written the first 3, and after of the other 6 I wrote 2 explicitly, and there are 4 more. So let us look at this. I have u alpha 1, u beta 1 star, u alpha 2 star, u beta 2, and here I have the complex conjugate of that. And similarly, here I have e power I e2 minus e1 t, and here I have the complex conjugate of that. So, obviously these two terms are complex conjugates of each other. But I have before we try to evaluate this, consider Z1, Z2 star plus Z1 star, Z2, where Z1 and Z2 are two independent complex numbers. So this is x1 plus iy1 times x2 minus iy2 plus x1 minus iy1 times x2 plus iy2. Now Z1 star Z2 is the complex conjugate of Z1 Z2 star, so I know that the answer should be real. So I know that the imaginary terms on the right hand side will cancel out, and the real part will be 2 times x1 x2, but iy1 times minus iy2, that is real. So this is the extra thing we are getting in the 3-flavor oscillations compared to 2-flavor oscillations. In the case of 2-flavor oscillations, the terms coming from the mixing are purely real. So we just took the real part of the phases. But now we have the mixing coefficients partly real, partly imaginary, and of course phases are partly real and partly imaginary, and they are getting multiplied. So we need to take the real part of the product. So we have this extra term coming in. And So based on that argument, we'll find that the probability of nu alpha going to nu beta at time t is equal to sum over I mod u alpha I square u beta I square plus 2 times sum over I, but with the condition that I should be less than j, real part of u alpha I u beta j rather u alpha I u beta I star u alpha j star u beta j times cos of Ej minus Ei times t plus 2 times sum I less than j imaginary part of u alpha I u beta I star u alpha j. Oh, sorry, this will not be plus, but this will be minus. The reason I put there, I wrote 2x1 x2 plus y1 y2, but I wrote z1 z2 star plus z1 star z2, whereas here I am considering z1 z2 plus z1 star z2 star, because of which it will be, if I do that, then this will be x1 x2 minus y1 y2. So that is why I have a minus sign. So this is the extra term which is coming in my oscillation probability. This leads to an important and as in the two-flavor oscillation case, I add and subtract this term, that is twice real this one. If I do so, then one term combines with this and I get mod u alpha I rather I get this. I get that, and this term now becomes 4 not plus, it is minus. The addition, when I add, that is going here, the subtraction term is coming here. So I have this coefficient times 1 minus cosine, and there will be a negative sign in front. Real u alpha I, u beta I star, u alpha j star, u beta j sine squared Ej minus Ei t by 2 plus 2 I less than j, imagine v power u alpha I u beta star no 2 here. This is sine. Sine squared means there will be a 2, 1 over half, but for sine there is no. And notice that if beta equal to alpha, I am considering survival probabilities. If I put beta equal to alpha, I have u alpha I star, which is mod square, and u beta j star, u beta j, which is mod square. So imaginary part of this will be 0. So there is no third term in the imaginary part. And also by the unitarity of u, first term is 1 if beta equal to alpha, 0 if beta not equal to alpha. So we write the first term as delta alpha beta. And it looks a bit funny, the negative sign in, if beta is not equal to alpha, the first term it has a negative sign, and probability with a negative sign looks a bit funny, but you don't have to worry about it because those matrix elements, some of them will have the appropriate negative signs so that the final probability will be a positive quantity. Now let us pay some attention to that third term because that has important physical consequences. In particular, let us look at P alpha beta minus P beta alpha. And the fact that I am writing this, I am assuming that beta is not equal to alpha, because if beta equal to alpha, this automatically vanishes. So if beta is not equal to alpha, the first term is 0. And you see that the second term is the same for both, because if I exchange beta and alpha, whatever product I had originally, I get the complex conjugate of that. And real parts of complex conjugates are the same. So the second term cancels, but the third term adds. So this will be 4 times imaginary u alpha I u beta I star, and it is not 0. So physically, what does it mean? That the probability alpha going to beta means think of it as some kind of chemical reaction. Reaction going this way, beta going to alpha means reaction going the other way. So the rate of reaction going this way is not same as the rate of reaction going the other way. Of course, here there are no energy imbalance. Usually in chemical reactions, that's what happens. Because of the energy imbalance of the states, reaction goes this way or this way. Usually, very rarely, there will be an equilibrium. But here there is no such thing. We expect equilibrium, but we find that if U is complex, the rate of transition from alpha to beta is not same as rate of transmission from beta to transition from beta to alpha. That is, the trine reversal invariance is not valid. And let us consider another situation. I consider the oscillation of, let's say, nu mu to nu e and nu mu bar to nu e bar. Now, based on the way I have written the mixing matrix, if I take the mixing of antineutrinos, then I have to take the complex conjugates of the mixing matrix. So, when I consider this probability, I have to replace all the mixing matrix by their complex mixing matrix elements by their complex conjugates. If I do that and take the difference, you will notice that the real part cancels once more and the imaginary part adds up. So this is also 4 times I less than j imaginary u alpha I u beta and star dot. So this probability also is non-zero. The difference between these two probabilities also non-zero, and this is a signature of what we call CP violation. CP invariance means particle properties are exactly same as anti-particle properties. So oscillation of neutrinos and oscillation of antineutrinos should be exactly the same. But if U is complex, then we find neutrino probabilities and antineutrino probabilities are different, and that means that nature makes a distinction between particles and antiparticles. And so this is the big question in neutrino physics now. Neutrino oscillation physics. Is there CP violation in neutrino oscillations or not? And the present generation of experiments and the future experiments, they are all designed to look for this CP violation. Okay, I will stop now. Yeah.
We are getting same results in both.
And that's a consequence of something called CPT invariance. See, I mentioned CPT invariance in the last class, where we said it guarantees that particle mass and antiparticle mass are exactly identical, not even a difference to 1 in 10 power whatever. So the same CPT invariance guarantees that the amount of CP violation and the amount of T violation should be the same. Okay, I will stop now, and in the next class I will discuss about how to measure these neutrino mixing angles and the CP phase delta. So we will meet next Wednesday at 9:30.